Drop a cup on the floor. Listen to it. The crack. The scatter. Pieces sliding across tile in every direction. Now wait. Wait for those pieces to fly back together. Wait for the cracks to seal. Wait for the cup to leap off the floor and land perfectly on the table. You know it won't happen. Everyone knows. But here's what almost no one can explain the laws of physics say it should. Every single law of physics we've ever discovered works perfectly in reverse. Gravity, reversible. Electromagnetism, reversibly. Nuclear forces, reversible. Run any equation backwards and it works just as well as forwards. So if every law works both ways, why does the cup only break one way? Your phone is dying right now. Not because energy disappears, energy is never destroyed. That's the first law of thermodynamics. But something is happening inside that battery that can never be undone. The same thing that broke that cup. The same thing that makes your coffee cool down but never heat back up. The same thing that makes you age but never get younger. It's called entropy. And your textbook probably told you it means disorder. Feynman said, that's not the answer. The real reason time flows in only one direction, the real reason broken things stay broken, has nothing to do with the laws of physics. It has everything to do with a number so large that your brain literally cannot comprehend it. And a man who died trying to prove it. Let me show you. But this isn't just about cups and batteries. The real mystery is deeper than any physics experiment can show you. Watch the waves at the shore. They crash. They foam. They scatter across wet sand. Now imagine the foam gathering itself back together, rising up out of the sea, and falling back further from the shore. You'd laugh. If you ran a movie of the world in reverse, everyone would laugh because it looks absurd. But that laughter, that's actually a weak way to describe something far more profound. Think about your experience. Right now, you remember what happened yesterday, where you were, what you said, what you ate. Those memories are vivid, solid, real. Now try to remember tomorrow. You can't. You can guess. You can hope. You can plan, but you don't remember the future. That's not how your mind works. And it goes further. You feel like you can do something about tomorrow. You can choose, you can act, you can change what happens next. But yesterday, no one believes there's anything you can do about the past. Remorse, regret, hope. Those three words alone prove that past and future feel completely different, not just in physics, but inside your mind. Inside your experience of being alive. Now, if the world is made of atoms, and you are made of atoms, and atoms follow physical laws, then this obvious one-way experience should come from somewhere in those laws. Right? The most natural explanation, the one almost anyone would guess, is this. Somewhere in the rules governing how atoms move, there must be a built-in direction. Some principle that says things can only go one way. That the laws themselves carry an arrow of time. And that would make perfect sense. Except we haven't found it. In over a century of searching from Boltzmann's statistical mechanics in 1877 to modern quantum field theory, not a single law of physics has a built-in direction of time. Gravity, reversible. Electromagnetism, reversibly. Nuclear forces, reversible. Run any equation backwards, it works perfectly. If you filmed the planets orbiting the sun and played the movie in reverse, A physicist watching it would see nothing wrong. Everything would obey the laws exactly. The equations don't care which direction time flows. So here's the problem that should keep you up at night. Every law works both ways. There is nothing in the fundamental rules that says forward only. And yet everything you've ever experienced only goes one direction. Where does the one-wayness come from? If not from the laws themselves, then what? That's the question. And the answer isn't where you'd expect. Let me show you the details. Picture the solar system. Earth orbiting the sun. The moon orbiting Earth. Everything tracing smooth. Predictable curves through space. Now imagine you filmed it. Every planet, every moon, every orbit captured perfectly. And then you played the movie backwards. Here's the thing. A physicist watching that reversed movie would see nothing wrong. Not a single violation of any law. The planets would trace the same ellipses. The forces would match. The math would check out perfectly. Why? Because if you reverse the direction of time in Newton's equations, if you flip every velocity, reverse every motion, the gravitational forces don't change. Gravity depends on mass and distance. Neither of those cares which direction time is flowing. Let me make this precise. A planet moves in one direction around the sun. Gravity pulls it inward. The combination of forward motion and inward pull creates an elliptical orbit. Beautiful. Now reverse all the speeds. The planet moves the other direction around the sun. Gravity still pulls it inward, exactly the same. The result? Another perfect elliptical orbit. Just going the other way. You could watch that reverse solar system for 1 billion years and never catch it breaking a single law of physics. Not one. It's easy to prove mathematically the law of gravitation is completely time reversible. So gravity doesn't give us the arrow of time. The force that holds the entire universe together, that governs how galaxies form and how apples fall, it works equally well forward and backward. Okay, but gravity isn't the only force in nature. Maybe the arrow of time hides in one of the others. Let's check. Electromagnetism, the force behind light. Electricity. Magnetism. Every signal your phone sends or receives. Reverse time in Maxwell's equations. Everything works perfectly. No arrow of time. Nuclear forces, the forces holding atomic nuclei together. The forces powering the sun. Reverse time. Works perfectly. No arrow. What about beta decay, the process where a neutron transforms into a proton? Releasing an electron? This one's interesting. There is a tiny asymmetry in certain weak nuclear interactions. Physicists have studied it carefully. But here's the honest answer. That asymmetry is, in Feynman's words, a very unimportant phenomenon for most ordinary circumstances. It cannot explain why cups break. It cannot explain why you age. It cannot explain why heat flows from hot to cold. Think about that for a moment. You speak and your voice goes out into the air. It scatters, it fades, it doesn't come sucking back into your mouth. That everyday irreversibility, the kind you experience every second of your life, cannot be hung on the phenomena of beta decay. So where are we? Gravity reversible. Electromagnetism reversible. Nuclear forces reversible. Every fundamental law of physics we've discovered reversible. We have to look elsewhere to find the explanation. And the first real clue comes from something you've felt your entire life, but probably never thought about this way. Friction. Right now, the Earth is spinning slower than it was yesterday. Not by much, you'd never notice. But the moon's gravity pulls on the oceans, the tides drag against the ocean floor, and that friction imperceptibly, relentlessly is stealing the Earth's rotation. Every century, the day gets about 3 milliseconds longer. That's irreversibility you can measure from space. But you don't need to look at the Earth. You felt this your entire life. Push a heavy box across the floor. It slides. It slows. It stops. And it never ever starts sliding back on its own. Where did the motion go? Feynman's answer is precise. The organized motion of the box, all its atoms moving together in one direction, got converted into disorganized motion. Irregular, random, jiggling of the atoms in the wood and the floor. Heat. Tiny vibrations going in every direction at once. Organized motion became disorganized motion. And that is the clue. Every time you rub your hands together to warm them, you're converting organized motion into disorganized heat. That's entropy. Not disorder in some vague, poetic sense. A specific, measurable transformation from organized to disorganized. So we should look at this more closely. Let me take a simple example. Imagine a glass container divided in half by a thin barrier. On one side is blue water. On the other, clear water. Two neat, separate regions. Now remove the barrier. You already know what happens. The blue drifts into the clear. The clear drifts into the blue. Slowly, steadily, the whole thing becomes a uniform, pale blue. What Feynman called Luke blue. Beautiful word. Terrible situation if you wanted them separated. Because here's the thing. If you wait a minute, an hour, 1,000 years, the water does not, by itself, separate back into blue and clear. It stays mixed. Forever. Now, can you separate them again? Sure. You could use filters, evaporation, chemistry. You could unmix it manually. But here's what Feynman points out with surgical precision. If you do that, if you reverse it, you yourself are causing irreversible phenomena somewhere else. You're generating heat, using energy, creating more of that same disorganization in the rest of the universe. The key phrase is by itself. Left alone, things mix. Left alone, things don't unmix. That asymmetry, that one-wayness is what we need to explain. And to explain it, we need to understand something about what's available and what's not. Here's something that sounds impossible. The ocean contains enormous amounts of energy. Massive, almost unimaginable quantities of thermal energy in every cubic mile of seawater. Yet you can't run a ship on it. You can't power a city with it. You can't do anything useful with it. Why? Because the energy of the sea is all at the same temperature. And here is the key principle. To extract useful work from energy, you need a difference. Hot on one side, cold on the other. A gradient. Without that difference, without something hotter than something else, the energy is there, but completely unavailable. Nature never loses or gains energy. That's the first law of thermodynamics. Energy is always conserved. But the availability of that energy, that decreases constantly. Feynman had the perfect analogy for this. Picture yourself at the beach. You've got towels. Nice, dry towels. And then a sudden rainstorm hits. You're soaked. Everything is wet. But wait, your towels are only damp. They're wetter than dry, but drier than you. So you use one. You dry yourself off a little. The towel gets wetter, you get drier. So you grab the next towel. Same thing. A little drier, a little better. But then you discover something horrible. All the towels are damp, and so are you. Everything is the same wetness. And no matter how many towels you have, 10, 100, 1,000, there is no way to get drier. Because there is no difference between the wetness of the towels and the wetness of yourself. That's what happens with energy. When everything reaches the same temperature, there's nothing left you can do. The energy is still there. Every atom is still vibrating. But you can't use it because there's no difference left to exploit. Think about your phone charger. It does the same thing. It creates a difference-organized electrical energy on one side, your depleted battery on the other. Your phone uses that difference to run. When the difference is gone, when the battery reaches equilibrium, you're stuck. Like wet towels at the beach. Energy everywhere. Usefulness nowhere. So now you understand the principle. Energy is always conserved. But the availability of that energy, the differences that make it useful, those disappear. Always in one direction. Always towards sameness. But how does this actually happen? How does ink actually mix? Let's look at the molecules. Magnify the picture. Forget about blue water and clear water as liquids. Forget about ink and towels. Go deeper. Watch the atoms. What you see is this. Billions and billions of molecules, all jiggling, bouncing, colliding. Blue molecules on one side, the ones we started with. White molecules on the other. The barrier is removed. And what happens is exactly what you'd expect. Some blue molecules bounce into the white side. Some white molecules bounce into the blue side. Gradually, relentlessly, they mix. Nothing mysterious so far. But now, watch carefully. Pick any one collision. A single blue molecule hits a white molecule. They bounce off each other. Now run that collision backwards. The white molecule approaches from the opposite direction, hits the blue one, they bounce back the way they came. Is there anything wrong with that reversed collision? No. It's perfectly legal. It obeys every law of physics exactly. Newton's laws, conservation of energy, conservation of momentum, everything checks out. That one reversed collision is indistinguishable from a real one. Check another collision. Same thing. Perfectly reversible. Check 100. 1,000. Every single collision, taken individually, works perfectly in reverse. And here is the deepest puzzle of this entire video. If you watch too carefully, if you watch one molecule at a time, you can't understand it at all. Because every individual collision is perfectly reversible. There is nothing in any single interaction that says forward only. Every bounce, every deflection, every exchange of energy works exactly the same in both directions. And yet the whole movie shows something absurd. Play the full movie backwards. All the molecules, every single one reversing their paths. Perfectly legal for each one individually. But collectively, the mixed blue water separates. Clear water on one side, blue on the other. A sharp boundary appears out of nothing. Order emerges from chaos. Every physicist in the room would laugh, because that doesn't happen. But why doesn't it happen? Every individual collision in that reversed movie is legal. Every molecule obeys the laws perfectly. Nothing is violated. Not a single equation broken. The answer, and this is the answer to the entire video, is that it's not impossible. It is not against the laws of physics for molecules to bounce around in exactly the right way to separate perfectly. It's just unlikely. Unlikely is an understatement. With 4 or 5 molecules, you might see it happen. Wait around for a year or two, and random bouncing might separate them by chance. That's conceivable. But a glass of water doesn't have 4 or 5 molecules. It has 4 or 5 million molecules. And the probability of all of them spontaneously bouncing into a separated arrangement, every blue molecule ending up on one side, every white molecule on the other, is not small. It's not tiny. It's a number so close to 0 that the word impossible doesn't even begin to capture it. You would wait longer than the age of the universe, longer than the age of 1 billion universes, and it still wouldn't happen. Not because it can't, because it won't. The irreversibility you see, the ink mixing, the cup breaking, your coffee cooling is not a law of physics. It's a fact of statistics, a fact so overwhelming, so absolute that it might as well be a law. And that is the answer. The apparent irreversibility of nature does not come from the irreversibility of the fundamental physical laws. It comes from the characteristic that if we start with an ordered system and have the irregularities of nature bouncing, the thing goes one way. That statement is the answer to the entire video. Let me make sure you hear it clearly. The irreversibility of nature cups breaking, ink mixing, coffee cooling, you aging, does not come from the laws of physics. The laws are perfectly reversible, every single one of them. It comes from statistics. Start with something ordered, molecules separated, cup intact, energy concentrated, and let the random jiggling of nature do its work. The system moves toward disorder, not because a law commands it, but because there are overwhelmingly more ways to be disordered than ordered. The odds are so staggeringly against reversal that it will never happen. Not in principle, in practice. Ludwig Boltzmann first formalized this statistical view in 1877. He wrote an equation connecting the number of possible microscopic arrangements to a single macroscopic quantity. He called it entropy. But here's what makes this idea even more powerful than Boltzmann imagined. In 1948, 70 years later, Claude Shannon proved something remarkable. Information itself follows the same law. Losing data, forgetting, noise corrupting a signal, all of it entropy. The same statistics that explain why ink mixes explain why your files corrupt, why messages garble, why memories fade. And this is why your phone battery dies. Not because energy disappears, energy is never destroyed, but because the difference that makes energy useful gets smeared out. Your battery isn't losing energy. It's losing organization. The organized electrical potential that powers your screen, your apps, your connection to the world, it's spreading into uniform, useless heat, like wet towels at the beach, like ink in water. Energy is never destroyed. It just becomes useless. So the statistical answer is clear. Irreversibility comes from the overwhelming probability of disorder. But that immediately raises a deeper question. If everything moves toward disorder, if nature always shuffles, always mixes, always spreads out, then how did it get ordered in the first place? That question has a cost. And a human story. This idea that irreversibility is statistics, not law, has a name. And it has a cost. Ludwig Boltzmann spent his entire career defending it. He believed atoms were real. He believed entropy was statistical, not some mysterious fundamental force, but a consequence of counting, of probability, of mathematics. The scientific establishment attacked him for it. Ernst Mach, one of the most influential physicists of the era, called atoms a useful fiction. Wilhelm Ostwald insisted that energy, not atoms, was fundamental. That Boltzmann's statistical approach was wrong at the root. For over a decade, Boltzmann fought alone. Paper after paper. Lecture after lecture. The physics community treated him like a crank, defending an idea no serious scientist should believe. In September 1997, exhausted and isolated, Boltzmann took his own life. He was 62 years old. 3 years later, Einstein proved atoms exist. Everything Boltzmann had fought for vindicated. On his tombstone in Vienna, they carved his equation. 5 symbols. S in quadrativ. The equation that connects disorder to probability. The equation that explains why cups break and don't unbreak. Why ink mixes and doesn't unmix. Why time flows in one direction. Hold something warm right now. A coupe. Your phone. Your own hand. Feel the heat? That warmth is entropy in action-organized energy becoming disorganized. Boltzmann's equation describes exactly this. And it will never reverse. So the question remains, how did the universe get ordered in the first place? Before we answer that, let me clarify something. When I say ordered, I don't mean neat or tidy. I don't mean aesthetically pleasing. In physics, ordered means distinguishable, the parts are separated, concentrated, arranged in a way you can identify. Blue water on one side, clear on the other, that's ordered. Mixed together, disordered. You might prefer the mixed version. You might think it looks prettier. Doesn't matter. The physics definition is about distinguishability, not beauty. Now here's the key reasoning, and it applies far beyond ink and water. If I show you a glass of partly mixed ink, some blue streaks still visible, not fully uniform, you can immediately conclude something about the past. It must have been more separated before, more ordered. Because things mix forward in time, not backward. Think about what that means. A physicist uses the laws of motion to predict the future. Where will the planets be tomorrow? But a geologist looks at rock layers and predicts the past. A historian reads documents and reconstructs the past. An astronomer looks at distant light and infers what happened billions of years ago. All of these sciences, every single one, work because the past was more organized than the present. Consider Napoleon. How do we know he was crowned emperor in 1804? Because multiple independent documents record it. If you check one history book and then another, they agree. The same date, the same event. That agreement, that consistency across independent records is only possible if the past was more ordered. If the universe had always been mixed up, if disorder was the eternal state, no records would be consistent. No memories would be reliable. no science of the past would work. The only way to explain the success of geology, history, astronomy, the success of every science that looks backward is to accept that the past of the world was more organized than the present, more separated, more concentrated, more ordered. That's not a law of physics. It's a fact about the universe we live in, and it needs an explanation. Some physicists have proposed one, and it sounds clever at first. The idea is this: maybe the universe is, and always has been, a vast soup of randomly jiggling molecules. No beginning, no special starting point, just eternal, aimless chaos. And occasionally, by pure chance, a small region fluctuates into an ordered state. Stars form, planets cool, life emerges. And we conscious beings happen to exist during one of these rare fluctuations, watching it dissolve back into chaos. Under this theory, our entire observable universe is just a statistical accident, a brief pocket of order in an ocean of disorder. We're watching the fluctuation undo itself, and that's why we see entropy increasing. That's why things mix and break and cool down. We're watching the accident correct itself. It's elegant. It requires no special initial conditions. No explanation for why the universe started ordered, because it never really started at all. But this idea is wrong. And I think it's not just wrong, it's spectacularly wrong. Here's why. If we are living inside a random fluctuation, then the most likely fluctuation that could produce us conscious beings capable of observing would be the smallest possible one, the minimum amount of order necessary. Just barely enough. And that means everything outside our immediate observation should be disordered. Random. Mixed up. If you look at a new star you've never observed before, the fluctuation hypothesis predicts it should look nothing like the stars you already know. It should be a mess. Because the cheapest fluctuation wouldn't waste order on things you haven't looked at yet. But every time we point a telescope at a new star, every time we look further into the universe, we find the same patterns. The same laws. The same organization. Distant galaxies look like nearby galaxies. Ancient light obeys the same physics as light in your room right now. Every new observation shows more order, not less. Every prediction based on a universally ordered past succeeds. As Feynman put it, the success of all the sciences that look backward tells us the world did not come from a fluctuation. The universe's order is not a statistical accident. It's real. It's everywhere. And it goes all the way back. And we don't need to guess anymore. The cosmic microwave background radiation, left over from the Big Bang, is a direct snapshot of the universe's beginning. In 2018, the Planck satellite measured it with extraordinary precision. What it found was unmistakable. The early universe was in an extraordinarily low entropy state, almost perfectly uniform, almost perfectly ordered. Not a fluctuation, a genuine, universe-wide initial condition of remarkable organization. The Planck data doesn't suggest this. It shows it. A photograph of the universe 380, 000 years after the Big Bang. And what you see is a cosmos almost impossibly smooth, almost impossibly ordered. The very thing Boltzmann's equation requires, the very thing Feynman said we must assume is there. Measured. Confirmed. Recorded in light that has been traveling for 8 billion years. The fluctuation hypothesis is dead. The universe started ordered. That's not philosophy. That's data. And that means we need something else, something beyond the laws of physics as we currently understand them, to explain why. So here it is. The statement that makes all of this work. It is necessary to ADD to the physical laws, the hypothesis that in the past, the universe was more ordered in every way than it is today. More separated. More concentrated. Lower entropy. Notice what just happened. We went through every law of physics, gravity, electromagnetism, nuclear forces, and none of them distinguish past from future. We proved that irreversibility comes from statistics, not law. We destroyed the fluctuation hypothesis with observation and data. And after all of that, the answer requires something outside the laws of physics as we know them. An initial condition, a statement not about how things develop, but about how the universe started. This statement is lopsided in time. It says the past was different from the future, but it doesn't come from the equations of motion. It comes from somewhere else, from the boundary conditions of the universe itself. And perhaps someday, that initial condition will become part of physical law. Perhaps we'll understand why the universe started ordered. But right now, we don't. We just know that it did. That's intellectual humility at the deepest level. The answer to why is time, one-directional, is because the universe started in a special state and we can't yet explain why. Now there's something I want to show you, something that demonstrates exactly how an irreversible machine really works. But first, let me state the law clearly. Everything we've discussed has a name. If things are at different temperatures and left to themselves, they become more and more the same temperature. The availability of energy perpetually decreases. This is the entropy law. Entropy always increases. Or to say it another way, the availability of energy always decreases. The one-wayness is always the loss of available energy. And in 2012, physicists confirmed something extraordinary. Landauer's principle, an idea proposed in 1961, was experimentally verified. Erasing one single bit of information, just one, generates a minimum amount of heat. Information is physical. Deleting data produces entropy. The same statistics that explain why ink mixes explain why your hard drive generates heat when you clear it. Thermodynamics, information theory, computing, all connected by one law. Entropy. Energy is never destroyed. It just becomes useless. Now let me show you a machine that proves this. Imagine a tiny device. A wheel with sawtooth edges like a gear, but with teeth that slope gently on one side and drop sharply on the other. Pressing against this wheel is a small lever, a pawl held by a spring. The pawl clicks into the teeth and allows the wheel to turn in one direction but not the other. This is a ratchet, and it only turns one way. Forward click, click, click. Try to push it backward, and the pawl catches. Locked. Now here's the clever idea. Connect this ratchet to a set of vanes, like tiny paddles sitting in a box of gas. The gas molecules are jiggling randomly, bouncing off the vanes from all directions. Most of the time, the hits cancel out. But occasionally, by random chance, more molecules hit one side than the other. The vane gets a tiny push, and the ratchet only turns one way. So every random push in the forward direction gets captured, click. Every backward push gets blocked. Over time, the wheel should turn steadily in one direction. powered by nothing but random molecular motion. Free energy. From randomness. Perpetual motion. Sounds too good to be true. And it is. But we have to look at the details to understand why. Here's what actually happens. The Paul is a physical object. It's tiny. It sits in a gas of jiggling molecules just like the veins do. When it clicks against a tooth, it bounces. That bounce generates friction. Heat. And that heat goes into the Paul's surroundings. Now the Paul itself starts jiggling. The spring holding it vibrates. And sometimes randomly, the Paul bounces up off the tooth, just as a molecule pushes the wheel backward. The ratchet slips. So what determines the direction? Temperature. If the gas on the van side is hotter than the gas on the Paul side, there's a temperature difference, and the wheel turns forward. Energy flows from hot to cold, and you get useful work. Exactly as the entropy law says. If the Paul side is hotter, the wheel turns backward. Energy still flows from hot to cold, but now in the other direction. And if both sides are the same temperature, the wheel goes nowhere. Forward clicks and backward slips happen equally often. Perfect balance. No net motion. No free energy. No perpetual motion. That's the technical demonstration. The phenomena of nature only go one way as long as they're out of equilibrium, as long as one side has a different temperature than the other. The moment everything reaches the same temperature, the directionality vanishes. No difference, no direction. No gradient, no arrow. The one-wayness of nature requires something to be out of balance. And that brings us back to where we started. Here we have an example where an obvious effect, the irreversibility of time, is not an obvious consequence of the fundamental laws. It takes a lot of analysis to understand why. Think about what we've done. Your memory, your sense of past and future, the difference between hope and regret, the fact that broken things stay broken. All of this, every bit of it, is completely involved in the statistical behavior of atoms. In entropy. In the initial conditions of the universe. And yet understanding that connection is not immediately available just by knowing the laws. The laws of physics do not have direct, obvious relevance to experience. Feynman gave a beautiful analogy for this. Consider a glacier. You can watch it move slowly, massively, grinding through a valley over centuries. To understand why it moves, you'd need to know about the hexagonal crystal structure of ice, how individual crystals slide against each other under pressure, temperature gradients, friction, melting points. The glacier's behavior comes from crystal physics. But you don't see hexagonal crystals when you look at a glacier. The connection is real, but it takes work to find. And nobody knows enough about ice crystals yet to fully explain every detail of how glaciers behave. The knowledge exists at one level. The consequences emerge at another. And connecting them takes time, patience, humility. Nature, it seems, is designed so that the most important things in the real world, irreversibility, memory, the arrow of time, life itself, are complicated. Accidental results of many laws working together. Not simple, not obvious, but deeply, profoundly beautiful. So let me bring this all together. We started with a cup hitting the floor, a crack, a scatter, pieces everywhere. And we asked, why doesn't it fly back together? We checked every law of physics. Gravity reversible. Electromagnetism reversibly. Nuclear forces reversible. Every fundamental equation works perfectly in both directions. The laws don't care which way time flows. So the one-wayness doesn't come from the laws. It comes from statistics. From the fact that there are overwhelmingly more ways to be disordered than ordered. A number so large that the word impossible doesn't begin to capture it. Not because the cup can't reassemble, because it won't. And behind that number stands a man who fought his entire career to prove it and didn't live to see the world agree. Ludwig Boltzmann. 5 symbols on a tombstone in Vienna. S. Clog vous. But statistics alone isn't enough. You also need a starting point. The universe began in an extraordinarily ordered state, confirmed by the cosmic microwave background, measured by the Planck satellite, recorded in light that has been traveling for 8 billion years. That's not philosophy. That's data. And why did the universe start ordered? We don't know. Not yet. That question remains open, perhaps the deepest open question in all of physics. That's not weakness. That's honesty. And honesty is where real understanding begins. Hold something warm right now. A cup. Your phone. Your own hand. Feel the heat leaving. That warmth is entropy-organized energy becoming disorganized. It will never reverse. Every second, everywhere, the universe is losing what makes energy useful. Energy is never destroyed. It just becomes useless. Everything I've told you today is sourced. The lectures, the experiments, the data. Links are in the description. If I got something wrong, tell me. Leave a comment. I will correct it. That's not weakness. That's how science works. That's how this channel works. And if this video changed how you see a broken cup, if you now understand why things only go one way, do something for me. Pick up a warm cup of coffee tonight. Hold it. Feel the heat leaving your hands. And remember, you're feeling the arrow of time. Boltzmann's equation. The deepest asymmetry in the universe. In your hands. Next time, on Feynman physics, we're going even deeper. Because light doesn't just travel from A to B. It takes every possible path between them. All of them. Simultaneously. And the reason it seems to go straight, the reason anything in the universe seems predictable at all, is one of the strangest ideas Feynman ever had.